So hello everyone. I'm Yann. You pronounce my last name how you want to pronounce it, but it's so in French it would be léger. And I'm going to speak basically about high performance LLMs. It's actually a topic which we already started to speak about. I'm going to speak a bit about the stack which is behind it. And the other topic which I'm going to try to cover, if the elements are with me, is doing a live demo of our serverless deployments. So it's going to be risky if we look at the network issue we had, but bear with me, we'll try to make it happen. For context, I'm the co-founder and CEO of a company called Koyeb. Basically, I spent the last 14 years building cloud infrastructure. I built 2 other cloud service providers before, called Outscale and Scaleway. And since 2021, we started this company and this product with serverless cloud infrastructure, and we added the AI component this year. So our focus has always been on simplifying application deployment from a general standpoint. And we'll be talking a bit about like the different things we do. Before I go to the demo and the technical detail, you, I think, pretty much aware of the context. The problem we're seeing is like there is an increase in the need of cloud infrastructure. The number I mentioned here, the 500%, is a study which is on the projections of the power usage of data centers. So the expectation right now is that it's going to grow 6-fold in the forthcoming years. The power needed, and it's only in the US. So that's a massive problem. So we believe there is a huge efficiency problem behind this. One of the reasons is there is no virtualization in high performance computing. If you look back 20 years ago, we had kind of the same issues with traditional CPUs, and we're facing similar issue, but now with GPUs. We're aiming to improve that, and we're providing a high performance serverless platform. The serverless components is purely a topic of efficiency, both like productivity on one end, and the other end is efficiency in terms of cost. We are trying to bring several different features. One is container continuous deployments. That's our roots. We started with pure compute on CPU. We do the same thing with models, and we do this on high performance hardware. We bring an experience where you don't have to have any infrastructure management, and we're letting you deploy globally to improve performance. So, and at the end of the day, the target for us is for you to get native resiliency and scalability. Our product lets you deploy AI apps end-to-end across multiple regions. So we let you deploy inference APIs. We don't do training. It's not our focus. You can do fine-tuning on our platform, but we don't do large-scale clusters. You can do some training with batch jobs. You can run a vector database, not as well as Pinecone. We're not like a professional, like high-skill vector database, but it's probably enough like for a lot of cases. It's backed by Postgres technically, and we let you also deploy traditional web apps and microservices. That's how we started actually. On the global side, we have 6 core locations, 10 data centers, and 250 edge locations. So the end game is to reduce latency to end users. If you're deploying a real-time application, you probably will care about like the 200 milliseconds of latency depending on where the compute is. So, and now it's going to be the truth moment where we'll be deploying a VLLM application live, and we're going to do some auto-scaling together. So we're going to deploy a Llama 3.1 inference endpoint on one end, and we'll launch some load and see auto-scaling in action. So if we go to koyeb.com deploy/VLLM, we can. So if you're not familiar with VLLM, it's an inference engine. You have a few classical inference engine we use on one end to deploy quickly if you don't care about performance. And I'm not saying they are not performant, but it's not their core focus. We use Ollama because it works across like a variety of hardware. So you can use Ollama and switch between CPU and GPU in actually 2 minutes. Or you can run with VLLM and do high performance inferencing. If I hit deploy, basically I'm going to land on our control panel. We see that actually technically it's just a Docker image. I'm going to maybe zoom in a bit more. So it's simply a VLLM image. You can customize the deployments. You can pick your model. We'll take the default one on this deployment. You have a few environment variables that you can tweak. We don't need a token because it's the default image. It's built in. And you can pick the hardware. For this deployment, we'll go with the small RTX 4000 GPU. It's actually deployed in Frankfurt, in Germany. We could change the location, and we'll set up autoscaling. And basically, we're going then to do the autoscaling work for you. So you have different criteria to set up the autoscaling. We'll pick the number of concurrent requests because it's more accurate. I mean, if you use CPU usage on a GPU-backed model, you're not going to see a lot of autoscaling happening. We are going to set it at 2 to be pretty reactive. And I think we're going to be good for now. We could set up some else checks. I think like the default is going to be good enough. We have the estimated cost at the bottom. And if I hit deploy, it's going to spawn a VLLM endpoint, basically, and it's going to autoscale depending on the load. So this should take like 1 to 2 minutes, basically. I have another deployment which I made before with a full Llama 3.1 model. It's here. We can check what it is. And this one is, so it's a custom image. The model is embedded to make it faster, actually, and to leverage caching on the hardware. We are using our A100, and it's autoscaling between 1 and 3 instances. This one is a bit more expensive because A100 are more expensive. But that's the principle. So if we look right now, we are going to see some logs of this deployment. We see that 1 instance is healthy, the 2 other ones are stopped. There are some past logs of my tests. And what I'm going to do is simply trigger some load. Get ready for, and let's hope the network is all right. And basically, what you should see, no, I don't want to close, in a couple, is, so it's a command line, which is actually triggering some load. So we're doing load testing with 5,000 prompts. There is a data set that we give, and there is the URL of the app which was deployed. So it's going to generate loads, or maybe, oh, it looks like it's doing it. So it's, whoa, that's fast. And now, that's actually way too fast. Sorry. Interesting. I think it's that's a network behavior. Interesting. Oh, and it's happening. So there is some lag somewhere in the testing because the prompt was buffered somehow on my screen, and even with the zoom share, you had some latency here. But the result is here, and basically it's created 2 additional instances, which are healthy and so actually it's probably going a bit too fast compared to the number of requests, but the number of instances increased. So that was the demo. It went through, and now we're going to dive into what's actually happening behind the scene here. All right. All right. So the story here is, so that's how I'm going to dive into our stack and what actually happened here. Our stack, we operate on top of parallel machines. So we have machines across like 6 continents. Depending on the continent, it's different providers. We operate on top of parallel machines, which are provided by different actors, depending on where it is. In some cases, we deploy our own hardware. In other cases, we partner with people who do have hardware. So that's a few of the names of the people who we partner with. On top of this layer, we have our own orchestration engine. The orchestration engine is using Nomad behind the scene, and it's actually creating virtual machine on demand. So we have a multi-tenant architecture. So if you are, as a customer, you will be on the same machine as another customer. And to ensure security, we use hardware virtualization. So we use either Firecracker, Cloud Hypervisor, or QEMU KVM, to which we pass the GPU. On the networking side, we use Cilium and Envoy for the load balancing layer. And that's actually what's part of what is giving us a metric to autoscale. And on top of this, inside of the virtual machine, you have our the container, which we deployed, and the VLLM engine, which is running inside of it. So the benefit of this is also that we are able to abstract the hardware. So if you look at what we deployed, I just picked a Docker image. I didn't have to pick the NVIDIA driver. It's actually embedded at the under layer in the virtualization layer in the VM we provide to the end consumer. And independent of the hardware, we are doing this work of abstracting the hardware. Our goal is to increase efficiency. So there is 2 things which come with this. This was mentioned before in the vessl.ai talk. We have auto-scaling and scale to 0, which are 2 key components. So auto-scaling is from 0 to x, scale to 0 is back to 0. So that's one of the key change, the cold start phase. And this is implemented by just observing metrics, basically. So we collect metrics every 15 seconds from the virtualization layer and from the networking layer. So and we store this in Prometheus. And then from this, we take decision of auto-scaling. We trigger auto-scaling every minute to avoid having flaps. And we actually only promote instances which are healthy, which you saw in the demo before with the healthy flag. One key thing overall, and it's like a constant for everyone, there is 2 limiting factors to auto-scaling. One is data transfer, and the other one is stocks. So data transfer is if you have to pull a model, which is a 400 billion model, or even an 80 billion model, you have like maybe between 50 and, I don't know, 400 gigabytes of data to transfer. And that's the core issue in all of this architecture. So we are working on caching system to optimize the transfers. And the second factor is stocks. So obviously someone needs to pay for the idling stock. So usually on demand is more expensive. We work around this on 2 aspects. We partner with multiple players. And we actually are looking to bring alternative hardware to market. And so that's our key focus for right now. So we have 2 things. We're looking to bring more accelerators to market. of people outside of NVIDIA so that we are not completely limited in terms of stock. And we are looking to optimize boot time so that auto-scaling is more reactive for end users.